good afternoon, or at this point, good evening. We are Nicola and Milena, and we're going to be, thank you, showing you Swisscom's internal, or not exactly showing you, but talking to you about Swisscom's internal knowledge graph for real-time customer impact calculation. We're going to go over our product and how it's implemented before going into an introduction to graph machine learning, and then finishing up with two problems and their solutions that we've worked on in collaboration with the Swisscom Digital Lab and EPFL, and some people who are here in the room with us as well today. So a little bit about us. We're from Swisscom, which hopefully you know as the leading telco provider in Switzerland. For us, it's really important to retain customer trust, and in order to do that, we have to provide a high level of reliability and also respond basically instantaneously to customer issues. More specifically, we work in DNAIA, which focuses on infrastructure analytics. We build internal tools for other teams within Swisscom so that they can stay on top of infrastructure issues and service quality. The two of us work in a product called Monty, where we enable end-to-end customer monitoring in real time and at scale. And we'll also talk about how we utilize graph embeddings for system understanding. So, what is the problem we're trying to solve? Swisscom manages many different networks with different access technologies that have different virtualized network functions, and we provide different digital product offerings for millions of customers. We have millions of network elements, hundreds of thousands of planned changes every year, and hundreds of billions of telemetry data points every day. So in an ideal world, all of this works perfectly. Systems are up 100% of the time, and our customers are so satisfied they don't even notice that we're there working in the background. However, in reality, this isn't always the case, and hopefully things don't go quite as wrong as this. These are severed cables. But we do work in a complex environment, and so when something inevitably does go wrong, we really need to know which customers are impacted, which customers aren't impacted, and what is the root cause of the issue. You as a customer, when something goes wrong for you, you want to know what's gone wrong, but also you really want the issue to be fixed as quickly as possible. In order for our customer support agents to be able to do that, they need to know where is the issue coming from. Is it in your building, the street, deeper in the network, and which team to send out to remediate it. So it can be very difficult to know which low-level device alert deep in the network is impacting you specifically as a customer, which service degradation is impacting you, or was it a recent change in cloud configuration that now you're having issues because of. The complexity only increases when we add on top of that root cause analysis, real-time or even future impact propagation. And that is where we come in as a solution. So when you call customer support with a problem, they'll take who you are, where you're calling from, and what your issue is. We call this the commercial customer base, the commercial or customer base. It's the entry point for customer support. It has a highly structured, it's highly structured. It is modeled in relational databases. It always basically looks the same. You'll have a customer with a contract at a location. What we show you with that information is everything else that's connected to that customer's location. We expose the different dependencies and connections between routers, switches, virtual network elements, etc. This is highly unstructured, and it will vary from location to location, product to product, and customer to customer. It all is housed in different systems, and it is dynamic and changes over time. We call this the impact topology. Why topology? Because it's a network topology, ++. And why impact? Because in it we show you the propagated impact of device alerts or impending configuration changes. This also allows the customer support agent to drill down deeper into the issue, see what other services or customers might be affected, and see whether actually the issue the customer is having is some high-level problem that's really obscuring something that's gone wrong deeper in the network. How do we do this? So we've said that there are many diverse systems in Swisscom. There are systems for network management, there are change management systems, router monitoring, core network monitoring systems, and so on. And if a customer support agent would have to go through all of them, they'd have to interact with a wide variety of portals and programs. And all of these things are expert solutions in their domain. Some of them are built in-house, some of them come from external vendors, and due to that, there is limited flexibility in how one can interact with them. That is, again, where we come in. We source many different systems. We divide them into stable data, which we call inventory, and transient, which we call alerting. And in all of those sources, we look for references to the same entity, because all of these sources, they can reference the same things. They'll call them by different names. They'll have different meanings in their ontologies, but they are essentially the same object, and this is a large part of what we do. Another important thing for us is that we provide real-time data. This is important not only for monitoring systems. Yes, you want to get alerts that are happening in real time, but also for the inventory systems. They are stable, but they are not static. And a support agent needs to know when a change has happened in the network. So we get all of our data in Kafka topics, ensuring that it is real time. We then transform and standardize that data into our internal data model. We don't only standardize it to our internal schema, we also provide a unified approach to life cycling. And we put this all into a graph database, which we then expose through an API and UI, and part of that UI you saw on a previous slide. We are actually working on something exciting where we are moving our graph from a graph database into the stream. And if you'd like to know a bit more about that, two of our colleagues, Sam and Michal, recently gave a talk at Kafka Summit, and Sam is hiding in the back of the room, so you can grab him later and talk to him if you'd like to get a bit more information about that. However, regardless of where it lives, a graph is a graph. Doesn't matter if it's in a database or on the stream. And in our case, it's a knowledge graph. We have different nodes and edges, different properties on those nodes and edges, and they all carry different semantic meaning. Our graph is constantly evolving, and what's important for us is that we use it to link inventory stable data and the observed more transient states, and we do this all in real time. You might ask why a graph, why a knowledge graph, or why a graph at all. A large part of what we are modeling is a physical network, and as the name itself says, it's a network or a graph. So when looking at how impact can propagate through it, it is intuitive to model this as a graph traversal, as traversing over edges, than it is anything else. And it's not only more intuitive, it is also more scalable and performant to model this as a graph traversal rather than a bunch of table joins. What we do by building a graph is we do a join on write as opposed to a join on read. The joins that we would have to do would be pretty non-deterministic, of variable length, and this can be very complex. Why a knowledge graph? As said, we are taking a lot of different systems, and they all have very different things that they monitor or govern. So we cannot model a port the same way as we model a contract. We cannot model a router the same way as we model a customer. This is why we need a schema that encapsulates all of these entities. Not only do we use the knowledge graph to be able to have different entities and properties, etc., it also provides us a valuable way of keeping systems correlated but still separate. It means that we will not have a situation where a monitoring system will tell us to delete a router. And additionally, it gives us a flexible way to represent our data that's also extendable. We work in a constantly evolving environment, and we need this functionality. So, in conclusion, we use a knowledge graph because it allows us to encode implicit knowledge and enables reasoning in a complex environment. For us, that means deriving impact from alerts and changes to customers and products. And with that, I hand over to Nicole.
Thank you, Milena. So as Milena explained, we have a huge knowledge graph that is in production. It's a real-time graph, and it takes more than 2 of us to actually build it. We have a couple of years of experience with that. But we would also like to apply some machine learning on top of that, but doing machine learning on top of graphs actually is slightly different. And let's have a quick introduction to graph machine learning and its challenges. So Of course, as with any other machine learning solution, we need to consider what data we have, what data we can use for machine learning. And with graphs, it's a bit tricky because it's not that clear what are the samples in our data sets, what would be the features, and how does that work. We just have one huge knowledge graph, and we can't just put it as a whole into a machine learning model. So we can take the network science perspective, and we can consider the node degrees, random graphs, just graph traversals, and this is very statistical and probabilistic approach, and it works quite well for homogeneous graphs. So if we just consider the routers, this works. However, as we mentioned, we are dealing with a knowledge graph, and this means that we have different kinds of entities. We have customers, we have incidents, we have routers, and those entities have different kinds of relationships within each other. Some of the relationships between entities are symmetric, some are transitive, and this is all now getting a bit closer to logic systems and needs to be considered when we are dealing with the heterogeneous graphs. So there is this bridge between heterogeneous and homogeneous graphs, and we are kind of using the knowledge graph as a base and then derive a topology from it. So what are the challenges of machine learning on graphs? In classical machine learning, we usually get a data set that has very clear samples. We have fixed set of features, and this is machine learning 101, and this is easy. Of course, machine learning has been applied to more interesting data. It has been applied to images, to text, and convolutional neural networks, deep learning solves that. That is also something that we can do. However, graphs are different because if you shuffle an image, it becomes a completely different image, and we usually don't expect from machine learning models to deal with this kind of data. Those are two different images. However, for graphs, if you reshuffle a graph in its visual or matrix representation, it's still the same graph. And this is something that we do expect from machine learning models to reason about and to treat them as humans would. So this is why these permutations are kind of making machine learning on graphs a bit more tricky. This is something that is sometimes called permutation invariance, and it breaks classical machine learning. We need to do something different. And one solution to that is graph representation learning, where we take the local and global node features and then produce embeddings, and this is kind of a bridge from graph data to machine learning as we know it. And one of the earliest approaches to that is node to back. The idea there was to start from a node and then have a random traversal from it, concatenate the IDs that we observe on the path, and just apply it word to back. And this is really from the GitHub repository how the reference implementation was done. And it provides okay results. We have some embeddings. That was the start, but of course this evolved further, and then we today have graph neural networks that can consider both local and global node features, and they are based on message passing. They really take the features from the neighborhood of the node, they transform them, combine them, and produce much richer embeddings. Then something else that is important to be mentioned is that here we are talking about node embeddings, but of course we have a question, how do we do graph embeddings? And similar to sentence embeddings, where we take the average of the word embeddings, the same thing works for graphs, which are somehow aggregate the node embeddings to represent a graph embedding. So, okay, we have some solution how to bridge the gap between graphs and machine learning. So what can we do with it? And as we mentioned, we have huge graph. It has a lot of data. It has different data, and we need some support to understand it and find the problems in it. Another thing is, how do we observe the graph as a whole? And this is another opportunity where we are experimenting with machine learning. And finally, we are providing internal service in Swisscom, and we need to rely on good data quality because we need to trust our system. There are, of course, some strong requirements that we set for our solutions. For instance, we have limited hardware resources because we want to run this in production eventually. Explainability, as I said, people will not trust our results if we cannot explain them. And finally, generalization, because we have not much labeled data, if any, and if we invest into labeling this data, we would like to generalize from there and apply it to the rest of the data that we have in the knowledge graph. So we have today two solutions that we will present. They were done in collaboration with EPFL and Digital Lab. We have Marie and Arnaud here as well. One solution is based on the similarity between graphs, and another is about abstraction. And the first one, done by Marie, is addressing the problem of the size of this graph. With size also comes the variety, and just navigating the different structures and patterns in this graph is something that is very good, an interesting problem to solve with machine learning. Another thing is that this is real-time graph, so it evolves and it can degrade sometimes, and we are very much interested into figuring out, okay, now something new appeared in the graph and it shouldn't be there. And finally, when we discover problems in the graph, in the network, in the data, we would like to see this on a more abstract, on a prototype level, because this is the level on which we can discuss it with architects and with the domain experts. So as I said, Marie implemented a solution as part of her master thesis called on the similarity of knowledge graphs. And here we considered a large set of the impact topology views, which are the subsets of the whole knowledge graph. We had several tens of thousands of such subgraphs, and then we compared, are they similar to each other, what are the common patterns, and such. This solution is based on the graph convolutional networks and contrastive learning. And big part of this solution was figuring out the data, because we assume that all data in our graph is good. And we don't really have negative examples when the data is bad, or we are not sure where it is. So what Marie did, she augmented the data set by constructing the negative samples and then trained the embeddings for that. For the data preprocessing, of course, here we considered the difference between heterogeneous and homogeneous graph and did the data cleanup. And we have very, very good conclusions here. The augmented data set worked. We now have good embeddings that are useful to us, but of course we should also consider the elementary statistical algorithms for that. If a customer has 0 routers, that is also a problem. So in these specific examples that we have on the slide, we have actually one customer, the same customer, but in 2 points in time. And the first, in the right side here, we have a new structure that appeared. This was actually by design. This is when we implemented the new feature in our graph, and it is good that we have it, but we are interested in the cases where this structure did not appear, because maybe this is a misconfiguration in the system, and this is a good demonstration how this system worked well. On the right part of the slide, we have the visualization of this vector space, and we can navigate it and find the examples that look a bit unexpected. Like here, we clearly have less data than in other examples. Here we maybe have too much data. It would be interesting to see why this customer location has this many network elements. So this is good indicators. But what is very important to mention here is that we need to trace it back to where this data comes from. We need to find it again in the knowledge graph, to find it which data source provided the original data, contact them, and figure out why this is happening. Without explainability, this is just a nice picture. So this is a very important point for us. Good. In this picture, I have a very large graph. You could consider that every pixel is one node, and we have around 2 million nodes here. However, unfortunately, this would be only like 1% of our graph, and we clearly have a problem. We need bigger screens. This doesn't work. And our solution here was, okay, let's consider how can we compress this big graph so it fits on one picture, and how can we then easier observe it? And this is the second master thesis that was done by Arnaud, who is also here with us. And this thesis had title Knowledge Graph Abstraction Layers, and it's kind of like zoom in and zoom out feature on our knowledge graph. So here the setup was slightly different. We considered the subgraph as a whole. So Marie worked with many smaller subgraphs. Here Arnaud worked with a huge subgraph of around 100,000 nodes. And then we considered how to compress it and how to visualize it. Here, this is also based on embeddings, and with embeddings and similarity between those vectors. If two entities are very similar, we can form supernodes by clustering, and this works even if we apply this solution iteratively. So we can have several layers of abstraction. Something that is very important to mention here is that very early we already observed limits in hardware. So important conclusion and solution provided here is that we need to deal with scalability issues, and Arnaud and Andre proposed a solution based on graph partitioning and Metis algorithm, and this works, and this is how we can deal with huge graphs and calculating embeddings for that. And here we have excellent demonstration of how it works in practice. So this is a graph of 1,000 nodes, and with their embeddings, we can find the nodes that are similar to each other. If they are similar, we can put them together. Then we can repeat the process and compress it further. Finally, we end up with less than 1,000 nodes. I'll just wait for the animation to finish. In the end, we end up with only 30 nodes, and 30 nodes are much easier to reason about than 1,000 nodes. And with the solution for scaling it further, we hope to visualize it easier as a whole. So finally, a few conclusions. Yes, for machine learning, we need to deal with the data. We need to consider the data problems. And when you work with graphs, you need to be careful. Is it knowledge graph? Is it uniform graph? And it works a bit differently. Of course, we have the usual machine learning challenges. We are working inside the company. This data is not publicly available, so we have limited access to label data. And finally, for future works, yes, embeddings look like a good bridge between graphs and classical machine learning. And we discovered this interesting relation between abstractions, compression, clustering, and embeddings. And with that, I would like to conclude the presentation. Thank you very much for your attention, and we can take some questions. Thank you.